Chris Elvidge. He's visiting us from Colorado School of Mines. He got his PhD in applied earth sciences from Stanford. And he's been working on detection of fires for over 30 years. An interesting stat here, his work has received over 40,000 citations, which is really impressive. Wow. And I would love to keep talking about his work, but I let him do it himself.
Yeah, okay. Okay, great. So we're at the Colorado School of Mines, but I actually started this work just over there at the NOAA building. I worked at NOAA for 25 years and retired in 2019 and moved my whole group and our algorithms and our data 20 miles south. So I'm going to talk today about the remote sensing of phases of combustion. And here is temperature. The temperature ranges for different things that are related to combustion. We have background down here, land, sea, ice, and clouds. When there's an active fire flaming, it is deriving its fuel from a process called pyrolysis. And pyrolysis is actually vaporization of lignin and cellulose and other components of biomass. And it's at a lower temperature than the flaming. And so the flaming provides the heat that drives pyrolysis. And so that's why I talk about wildfires as being a coupled system of an exothermic phase, that's heat producing, uses oxygen, produces heat, that's the flaming primarily, and endothermic, which are processes that require heat. And so down here, these are the endothermic processes, starting out with preheating, which drives the water off and gets the biomass ready for pyrolysis. Pyrolysis is actually just tearing apart the lignin and cellulose and other components of biomass to produce volatile gases that fuel flaming. Smoldering is the direct attack of oxygen onto carbon char. And so it's a little bit cooler than flaming. And then at the top there's flaring. That's things like gas flares. And they burn much hotter than the flaming phase of biomass. So why are we interested in this? Because these phases have different types and proportions of gaseous emissions and smoke. And there are different management and fire suppression approaches for flaming versus smoldering and pyrolysis. So it's information content that would be quite useful. And we've been doing research on this for more than 10 years. About the calculation of temperatures from any sensor, if the object fills the entire field of view, then you only need one spectral band, because these are the Planck curves. Here's wavelength and here's brightness. And so you see this regular progression as the object gets hotter. And as long as it's completely filling the field of view, those lines don't cross. But we have a different situation with data such as VIIRS, because it is perhaps the combustion source never even fills the whole pixel. And so this strategy of using a single spectral band to calculate temperature is a special case. It's when the object fills the entire field of view. And so what we developed are ways to get at temperature and other parameters, but it requires multiple spectral bands. Okay, so this is again a summary of the flaming versus non-flaming combustion and how they're linked. If you see flaming, there has to be pyrolysis. You might not be able to see it from space, but it has to be there. because that's what's fueling the flaming. And so this research traces back to 2013, when I had a project to investigate the remote sensing of peatland fires in Indonesia that was sponsored by the US Embassy. And I collaborated with remote sensing researchers at the Indonesia Space Research Institute, LAPAN. They've been since renamed. But the problem that they had was with that the sources of satellite observed fires couldn't make a distinction between flaming and smoldering, or flaming and pyrolysis. And so they had expressed interest that the US Embassy picked up on and said, well, maybe we could do some research to figure out what we can see from space regarding combustion phases. And our approach was to contact the US Geological Survey and ask them to collect nighttime Landsat data of active peatland fires in Sumatra and Borneo. And I'll show you what that data looks like in a moment, but we detected fires in both the shortwave infrared and longwave infrared. But the shape and intensity of the radiant emissions in those two spectral bands were quite different. And that was the discovery moment that there is an approach to studying and measuring flaming and non-flaming, particularly at night, in the using multiple spectral bands, shortwave infrared. At night, those spectral bands are designed for daytime imaging. And so at night, what they picked up, aside from the noise floor, are sources of heat. So yeah, we had a paper published. Here is a look at this nighttime Landsat. And on the left is the shortwave infrared at 2.2 microns. It's the band 7. And on the right is band 10, around 11 microns. And so when we looked at this data, we immediately recognized that these are two different combustion phases. You have in the long-wave infrared, that is the non-flaming component of the wildfire, of the fire. And so it's picking up on the long-wave infrared heat. We see some of the same patterns in the swir, but we could find cases where we saw something in the swir, but nothing in the long-wave infrared. And we found the opposite. There are cases where you see something in the long-wave infrared that really doesn't have an exact counterpart in shortwave infrared. And so looking at this is where we decided we can analyze some combustion phase differences within wildfires and improve the information content of our data products. After thinking about it many years, I decided, well, there has to be pyrolysis everywhere you see the flaming phase. This is the flaming phase, and we just can't see it. It's too small to be seen at the Landsat resolution. We have the same problem with VIIRS, only it's worse. Okay, so based on those observations, we developed a concept for a flaming subtractive method to strip off the flaming phase radiances and then analyze the residual. And this is the reason we were driven towards this analysis is that traditional satellite hotspots are dominated by the flaming phase. And so in addition to not being able to distinguish flaming and smoldering, what you do detect in a satellite hotspot is dominated by the flaming phase due to the temperature of the fourth power term in the Stephan-Boltzmann law. So we developed a concept for using the short wavelength channels to model the Planck curve for the flaming phase, which allows us to calculate the radiances in all the spectral bands, subtract that off, the observed radiances, and then analyze the residual for the presence of a lower temperature phase plus an ambient background. And this was our first attempt at that. And so this was in the Sumatra nighttime Landsat image. On the left, this is the actual radiances from Landsat. Here's the flaming phase Planck curve. And so we calculated that with the two shortwave infrared channels in Landsat. And that allowed us to calculate the radiances from the flaming phase in all the other spectral bands, particularly out here in the long wave infrared. We subtracted that off and we found that there's a residual. And so here's the radiance anomalies. This is the original data from long wave infrared. And then when we subtracted off the flaming phase, we saw these puzzling shapes of low radiance inside the thermal anomalies. And we were puzzled by them. And believe it or not, it took me years to realize it's because we didn't apply an atmospheric correction. And the shortwave infrared channels are in a spectral range that has very high transmissivity through the atmosphere, and that's not the case for long wave infrared. So we wanted to apply this to VIIRS, which is the Visible Infrared Radiometer Suite, flown by NASA and NOAA, and its primary mission is weather. There's a daytime image where you can see the land, the sea, and clouds, beautiful storm out in the Pacific Ocean. And VIIRS is famous for its ability to collect low light imaging data in near visible and near infrared. It's the so-called day-night band. And so many people are familiar with this day-night band, which with its incredible capabilities to see moonlit clouds and lights from cities and towns, and even lights from fishing boats. And what is less well known is the fact that VIIRS collects 4 daytime channels at night. So they are in the near infrared and shortwave infrared. And this turns out to be our key to studying flaming and non-flaming combustion with VIIRS. And so this is a wildfire in California back in 2018. Here's near infrared, shortwave, and shortwave infrared. And what you see in these bands is the noise floor of the sensor, punctuated by these pixels having high radiant emissions, primarily from combustion sources. And then as you get out in the mid-wave infrared and long-wave infrared, you're seeing the radiant emissions of the Earth, the land, the sea, the clouds, the ice, and then overprinted on that, if you know where to look, you can still see the combustion. And so our approach is to use these 4 spectral bands in the near infrared and shortwave infrared to model the Planck curve for the flaming phase, and then subtract the radiances from the flaming phase, add these longer wavelength channels, and then analyze the residuals. You know, and this is sort of serendipity because if a scientist like me communicated to NASA and NOAA saying, we'd like you to continue collecting the near infrared and shortwave infrared spectral bands at night, I probably wouldn't get a response. But this all traces back to an engineer he was the chief architect for the VIIRS instrument. And he, years after we got this started, he contacted me and told me how this happened, and because it had been a bit of a mystery. And so he says that he was anticipating that the midwave infrared would have some problems with saturation on large fires. And to mitigate for that, he recommended, basically wrote the instructions that the 2 near infrared and the first shortwave infrared spectral bands should be collected at night because he thought that they could be useful for the analysis of fires. Interestingly, he did not recommend that M11 be collected at night because he knew it would have a larger saturation problem. That's a spectral band, second spectral band in the short-wave infrared. So years later, we actually put in a request to change that policy, and it took about 3 years to get approved. And at the starting in 2018, this spectral band was added. Okay, so here's what this data looks like. This is the same pixel with 2 different algorithms. This is wavelength versus radiance. And the red asterisk indicates spectral bands with detection. And then we use these 3 long wavelength channels primarily to model the background. And so our first algorithm used these detections and it did what we call dual Planck curve fitting. So we were fitting a Planck curve for the hot object and the low temperature background. And that's how we solved this issue right here in the midwave infrared, where you've got a mixture of the signal from the background and the combustion. And so the way we allocate that is through this dual Planck curve fitting. We have a detector that's specific to detecting the presence of combustion in those 2 spectral bands. And here are the results for the same pixel using a different algorithm that uses these short wavelength channels to model the Planck curve for the flaming phase and subtract that from the original radiances and then analyze the residual for the presence of a secondary emitter. So you can see the temperature for the standard algorithm is 1076, background is 291 K, and the source footprint was 184 square meters. And over here, we have the primary temperature dropped a little bit from 1076, well, it went up a little bit to 1159. The footprint dropped a little bit, but then we have a secondary temperature, in this case, 607 Kelvin, and a footprint of almost 2,000 square meters. And this temperature is characteristic of flaming. This temperature is characteristic of pyrolysis. Okay, now when we do our calculations, we're using physical laws. And so we calculate the temperature using Wien's displacement law, which is a derivation of Planck's law. And it basically says that for your Planck curve, the peak in radiant emissions points to the temperature. And so we don't need a spectral band on that wavelength because we've got enough spectral bands that we can model the Planck curve and find the peak and calculate the temperature. The source area is calculated based on the ratio of the observed Planck curve amplitude versus the Planck curve for an object at that temperature filling the field of view. And so the Planck curves that we derive are always subpixel. And so once we know the temperature, we can develop a ratio between the amplitude of that observed Planck curve versus the amplitude of the Planck curve for an object at that temperature, and multiply that ratio by the pixel footprint size to estimate the source area. And then the heat output, or radiant heat, is calculated with the temperature and source area via the Stefan-Boltzmann's law. And I'm not sure if you're familiar with the fire radiative power that's calculated from MODIS and VIIRS data. Well, that traces its roots back to the Stefan-Boltzmann's law, but because they don't have temperature, they assume the temperature is 1,000 K. And so it's something about FRP that most people don't realize is that it's only correct if the object is at 1000 K. So anyway, we do it different. We calculate the temperature and source area and calculate radiant heat with a physical law. And it has the same units, megawatts, as fire rate of power. And so we wrote a paper about this. And I'm going to take you on a quick tour to look at some of the data. Here's from last year, the Brazil Amazon area. And you can see those colored marks. This is from our standard algorithm. And so the color coding relates to the temperature, with the lowest temperatures being purple. Blue is a little bit warmer. Green is still warmer than yellow. And then when you get a red color, that's almost always a gas flame. It's so hot. And so this is our standard output. We looked at an example a couple of slides back. It has two Planck curves, one for the hot object and one for the background. And right now we run both algorithms. And so we have another algorithm, VIIRS Nightfire version 4. And if we find a secondary emitter, oftentimes we don't find one, but when we do, we place a little black star inside the place mark. So you can find the ones that have a secondary emitter. And that here's the output for the same pixel that we just looked at, but from the different algorithm, with a Planck curve for the hot object, the flaming phase, a Planck curve for the non-flaming phase, then a Planck curve for the background. And so we kind of learned the hard way that we have to do an atmospheric correction. And so we first developed this method and applied it to nighttime Landsat with no atmospheric correction. We saw these dark patches inside the non-flaming phase. And it got us to think about why that happened. And it traces back to the transmissivity differences between the shortwave infrared right here. This is transmissivity versus wavelength. And so these red shapes are the VIIRS spectral bands. And the shortwave infrared is typically the clearest, has the clearest atmospheric windows. So when we model the Planck curve with the shortwave infrared, to get the flaming phase radiant emissions in the long wave infrared, our analysis was affected by the fact that we hadn't done an atmospheric correction. And you've got lower transmissivity out here in the long wave infrared. All right, now I'm going to talk about saturation, because it is absolutely essential that you not include saturated radiances in your Planck curve analysis. It just throws a real monkey wrench into your analysis. And so when you talk about the saturation problem in nighttime VIIRS data, or any VIIRS data, it traces back to the aggregation zones that are present in the formation of pixels. And so here's nadir at the edge of scan. And here we have a horizontal sampling interval. That's the distance between pixel center and pixel center. And here's the scan angle. So here's nadir, and here's the edge of scan. And so for the first part of the scan, 3 detectors are being averaged. And then there's a switch point. And then it goes down to 2 detectors, another switch point. And at the edge of scan, the pixel is formed from a single detector. And so all those detectors have the same saturation radiance. And so if you find a pixel that's fully saturated, it statistically it will occur more often at the edge of scan, because that's where you're generating, you only have a single detector contributing to the pixel. And there's a phenomenon called subpixel saturation, that it can't happen out here, but it can happen in here, in these two aggregation zones, where one of the detectors or two of the detectors are saturated. And so the resulting radiance is affected by saturation, but it's not, the pixel's not fully saturated. Let me show you what that looks like. Here is M10. Oh yeah, this is yeah. Okay, this is M10 radiance versus M11 radiance. For the image that covers the big fire in Los Angeles about a year ago. And so the way you can spot saturation is by comparing the radiances from a band that lacks saturation generally versus a band that's susceptible to saturation. And so you can see it starts out pretty linear and then kind of bends over. And so that's actually saturation radiance way up there. And so M11 is saturating on some pixels. This one is sub-pixel, but it's close to fully saturated. And then there are several pixels out here that have sub-pixel saturation. So we had to build methods into our algorithm to test for the presence of saturation. And so M11 has this problem to some extent. The spectral band that has this problem very frequently is M12. That's in the midwave infrared. And so this is a scatter plot of M13 radiance. M13 almost never saturates because it is a dual gain spectral band that was specifically designed to avoid saturation on wildfires. And so we use this band as the reference. We look at the M12 radiance, and again, we're looking for full pixel saturation and subpixel saturation. And we've got both of them in here. And so you can see this is very linear starting out, but then it starts to bend over. And so these are pixels that have subpixel saturation, and up here is full pixel saturation. All right. One of the things that we do with all this VIIRS data is to identify persistent infrared emitters. And so these are not wildfires. These are industrial sites, volcanoes, gas flares, and we have a catalog with about 20,000 of them. The new catalog is going to have even more. But once we know where those sites are, we generate a bounding vector. And as we get the new data coming in, if it falls within one of those bounding vectors, it gets added to the long temporal profile for that infrared emitter. And this one happens to be a steel mill in the Ukraine. And so the top panel shows the radiance in the shortwave infrared, M10. The middle is temperature, and down here is radiant heat. And there are a couple of things to note here. One is that when the war, shortly after the war began, this site terminated its activity, and it's never come back. You can see this is, okay, it was updated yesterday. And so we update these temporal profiles once a week. Another thing to notice here is this temperature change right there, starting in 2018. That is the effect of adding the second shortwave infrared channel. Prior to that, we only had one shortwave infrared channel, and we still fit the Planck curve, and we got temperatures. But what we discovered is that when we added the second infrared channel, well, we more than doubled the number of pixels where we could calculate temperature, because you have to have at least detection in at least two spectral bands to do the Planck curve fitting to calculate temperature. So you can see it's more dense over here than it was over here. and also that there was a shift in the temperature. And so anybody that uses this data should be aware of that. We've done the best that we can with what we've got available, but there's definitely a change when we got the second spectral band. Okay, so our global VIIRS Nightfire version 4 processing started almost 2.5 years ago. And it was 8 years after, it was 10 years after we developed the concept for the flaming subtractive method. And it just took us that long to work through the methods development and developing an in-house atmospheric correction that's based on Modtran. And so currently our success for finding a secondary emitter is about 50%. Now, to do the flaming subtractive method, we have to have detection in at least 2 shortwave infrared channels and then the 2 midwave infrared channels. And so that filtering step, it only about half of the VIIRS Nightfire detections have that condition where they've got both shortwave infrared and longwave infrared. And of those, only about 50% of the pixels test as having a valid secondary emitter. And we have to do filtering to identify these spurious secondary emitters. And so this is one of our areas that we're still doing research on. We want to raise that success ratio up. And so we're actively working on that. And it's definitely an important thing that we need to work on. All right. Well, I've got a little summary, and then we'll go look at last night's data. We produce VNF data globally from 3 satellites with about a 2-hour latency. Using spectral bands in the near-infrared and long-wave infrared, near-infrared to long-wave infrared, we derive Planck curves for infrared emitters, calculate temperatures, source area, and radiant heat with physical laws. The quickest way to get access to this data is with our email alerts. And so we have a way to deliver this data out to organizations or researchers that have an interest in it. They can also get a license to access the global data. There's a free academic license. And then we have several companies, I think there's 6 or 7, that pay us to have access to the data. And that's important to us because we're a soft money operation. So the VNF data extends back to 2012. And I showed you how we monitor industrial emitters. Currently, the data is being produced from 3 VIIRS instruments that fly on the SNPP satellite, NOAA 20 and NOAA 21. There are 2 more that have been built and are going to be launched. The 4th one is scheduled to launch in 2027, and then the final one will launch in 2032. And NASA and NOAA are already planning a follow-on sensor series that'll have essentially all the existing capabilities from VIIRS and perhaps improved spatial resolution, maybe even additional spectral bands. I'm not part of all of that, but I know it's going on. Okay, and so with that, I can respond to questions, and we'll take a look at last night's data. Any questions? Yeah.
Do you use specific algorithmic corrections depending on the satellite that you get the detections from? Like, does each satellite differ?
You know, we test for that, and we found that the data are there's they both go through the same process to have a radiometric calibration. And so we can't see any differences. And so the way we tested for that was to look at long gas flares that have been running for decades and see if we see a difference in the temperature or source size or radiant heat when we go from one satellite to the next. And we can't see any. And so we're aware that it could be the case, but we tested it and don't see any change, any difference. Other questions?
Yes. I was wondering, so I've read about the Beer's energy fraction concept, and they also it's a different method for detecting the nighttime fire combustion phase from Beer's. Are you familiar with that one?
No, I'm not.
Wang et al. Paper from 2020. They also use the Beer's day-night band and long wave infrared bands. But I guess I was wondering about the contrast with your approach, but maybe we can talk more about that later.
Yeah, I haven't looked at it.
Okay.
And we've also tested using the day-night band in addition to the near infrared and longer wavelength channels. And we realized that it's dicey because that spectral band picks up on electric lighting as well as combustion sources. And so we have taken a very close look at it and decided that what we found is that it throws off our Planck curve fitting and makes the object look like it's hotter than it really is. And it's because unless you unmix the electric lighting from the combustion source radiance, that's going to happen. And that is a tricky thing to do. And so I'm interested that there's somebody else that's working on this, but I haven't compared or looked at their results.
Okay, awesome. And a follow-up is if you've ever used your combustion phase results to I guess correlate with modified combustion efficiency to see if there's a relationship there.
You know, we would love to do that. And I'm always on the lookout for opportunities to do that kind of research. We're a really small group, and so we don't have the resources to do that ourselves. And so that would be something that we could do through a collaboration.
Thank you.
All right, here's last night's data. I've got both of the algorithms up here. So let's look at first at the standard algorithm. And here's a big cluster of flares in Algeria. I'm going to try and spot a case that has the pixel saturation. No, that one doesn't have it.
I think you're not sharing.
Oh, yeah.
Yeah.
You were screen sharing.
It's like nope.
So maybe you need to stop sharing
I think
that one.
I think
They're on the screen.
Yes. Let's see where we are. Right. So here's
Here's the share button. And we want to go to the Google Earth.
Okay,
This
one here?
Yeah.
okay, great.
Yeah, okay.
Why is it not online? It showed
Maybe
up
I have
online,
to,
but
maybe I
not.
have to shut down that PowerPoint.
Did you have to like drag it to the screen or something?
While we're fiddling around, any other questions? Okay.
Also submitted. There we go. Okay.
All
I
right.
don't know why that happened.
Yeah, okay. Well, I'm gonna try and find a detection that shows saturation so that you can see what it looks like. Not yet. Strike it out on saturation. I'll try one more. Yeah, it's almost there, but the saturation, typically, the first band to be affected by saturation will be M12. And so it becomes very obvious where the M12 radiance is substantially lower than M13. And so that's a tip off that you've got saturation. And so we test each pixel looking for saturation, particularly in those the M11 and M12. Well, I'm striking out. So let's go look at the other product, which is from the same night. And I'm looking for a case where there is a secondary emitter. Okay, well, I saw some up here. Let's see if this one has something that's got a secondary emitter. Yep, this one does. And so, oops, lost the screen.
It's back.
Oh, okay. So here's an example of a pixel that tested positive for a secondary emitter. And so we've got both algorithms running right now for all three satellites. Any other questions or discussion you'd like to have?
When you click on a point and like a bunch jump out from that, is
Yeah.
that different detections for the same like?
Yeah,
Oh, okay.
they're packed so close together that they only get pulled apart when you tap on the detection. And then there's something that we're still falling short on is glow. And here I can see glow. You're getting detections way out here, away from where the real flares are. Let's see if the other product has the glow. Yeah, see, this product, this is the standard product, and we're doing better with the glow. And so this is an oil field in Venezuela that is basically ground zero for glow. It is really chronic. And if you go to other parts of the world, it's not nearly as big an issue. Other questions?
Question about, so long-term comparison of fires using this.
Uh-huh.
So if the background, if we're getting more and more long-term emitters every day, and we're getting more wildfires over time, and we're seeing more and more interaction of those two through a time sequence. I'm
Yeah.
thinking like fires through time.
Yeah.
How do I maybe sort those two things out in it?
Yeah, well, the approach would be to run extractions on our time series because we have nightly data going back to 2012. We actually have a database. And so when we form the profiles for industrial infrared emitters, we're basically taking the incoming detections, and if they fall within a certain boundary, we affiliate them with that site. And so the same thing could be done for fires, and it could be done at a state level or around a region that is known for fire activity. So we've got the data, but when I ask for those sorts of profiles, well, we haven't pulled it together. And so it would be interesting to do, but it'd take a little bit of more work on our part to prepare the capability to generate long-term temporal profiles for wildfires. Like to do it. All right. Any other questions? Okay, well, you can track me down via email, and everybody in this room is eligible to get a free license to access this data. That's the best way that we have to ensure that the people that use it give us fair credit for developing the algorithms and generating the products. And we're always interested in having new collaborations on this data product. All right, well, thank you so much.